Let's consider the issue of ionization energy and the atom. Ionization energy is the energy it takes to remove an electron from an atom. As such, if you think about it, it must be related to Einstein's work function. The work function, recall, is associated with the photoelectric effect. If we pull a mole of electrons away from a mole of atoms, we have expended the ionization energy to get that mole of electrons. Now, atoms can have multiple ionization energies. The first ionization energy is the energy it takes to remove the first electron, if you wish the outermost electron, easiest electron to get. The second ionization energy is what it takes to remove the second electron once one is already removed. So we're taking an electron from a positive ion. And of course, the third ionization energy is the energy it takes to remove the third electron from atoms that have already lost 2 electrons. And that, of course, should be higher. If we see this diagram of electrons in the nucleus, we ask, what is the nature of the force that holds the electrons close to the nucleus? And I think you'll immediately see that that is a Coulombic force that is holding the electrons to the nucleus. The two factors that determine the size of this force. Well, we studied this. We studied this by experiment. The first, of course, is the number of protons. The more protons, the higher the force. The second is the separation distance between the nucleus and the electron that's being taken away. How does ionization energy then relate to the force holding the electron to the nucleus? I think it's clear that the greater the force holding the electrons, the higher the ionization energy. The greater the Coulombic attraction, the higher the ionization energy. What's the relationship between the force holding the electron to the nucleus and the number of protons in the nucleus? Again, the force is directly proportional to the charge. The higher the charge, the higher the Coulombic attraction and force. What's the distance relationship? Well, we studied that too. The force is inversely related to the square of the distance. So as we get closer to the nucleus, the force tends to increase dramatically the closer we get. Moving from left to right, say in periodic table row 3, what is the trend we see in nuclear charge? Well, it increases linearly as we go from left to right. In the same row, what is the force between the electron and the nucleus? Again, it increases linearly. And what should the first ionization energy do as we look from left to right? It should increase fairly linearly. Now, there are other factors that can enter into it. And as we might imagine, the electrons get a little tighter, a little closer to the nucleus as well as you go from left to right. And so there's a distance effect that might increase it more than linearly. Moving from top to bottom in group 1, the alkalis of the periodic table, what are we doing with the distance between the nucleus and the valence electrons? Well, as you can see, as you go from top to bottom, that will increase linearly. In the same group, what is the force between the electron in the outer shell and the nucleus? It decreases. Now, the decrease is not linear, as you can imagine, because of the Coulombic attraction versus distance. What should the first ionization energy do as we go from top to bottom? Again, it should decrease. Let's look at this and have a little quiz. The first ionization energy of lithium is 520.2 kilojoules per mole. As you know, this is in the second period of the periodic table that has 8 atoms. So, why don't you predict what you think the first ionization energy of fluorine will be 325, 1520, or 17,000. You might have chosen 1520, but actually because of the increase from 3 protons pulling until 9 protons pulling, the effect is actually greater than linear, and the first ionization energy of fluorine is actually 17,000 kilojoules per mole. We know, of course, that fluorine is the most electronegative of all the elements. It's tugging on its electrons, we might say even desperately. What about the first ionization energy for rubidium? Is it 325 kilojoules per mole, 403, or 1520? Again, comparing it to lithium at 520. Well, as you might expect, it's closest to 403 kilojoules per mole. It can't be greater because the distance between the nucleus and the outer shell rubidium is quite a bit larger than the distance between the lithium nucleus and that outer shell electron. In our last slide, we can see a chart from the University of California at Davis showing what happens in increasing ionization energy. As we might imagine, and as we've studied, as you go from left to right, the ionization energies are going to increase. And we're talking mostly first ionization energies here. And then as you go from bottom to top, the ionization energy increases. Vice versa, as you go from right to left, the ionization energy decreases, and as you go from top to bottom, the ionization energy in any particular chemical group will also decrease.